Good morning. Thank you, Professor Ishibashi, for inviting me in the conference. And it is a pleasure to be here. Well, I have been in contact and in collaboration with UEC since last 20 years. And I've been working on cold atom and Bose-Einstein condensation and quantum optics, quantum information systems. So, at present, I observe that my presentation will be different from previous talks because it's different from talking about AI or presenting the work on Internet of Things. I'm introducing a device which we can make using cold atoms and their interaction with the optical fields. So this work started during my days in Germany, and then I continued this work and published this work. So what we have up here is a recurrence tracking microscope. It's a position sensor which is for nanoscale surface scanning. Well, if we look at the microscope, so there are three different kinds of microscope for the purpose of surface scanning. One is optical microscope, which is the oldest one. It is based on diffraction, reflection, and transmission of light incident on a specimen. Then we have electron microscope, and it is based on the passing electron beam from illuminated specimen and producing an image. And the third one is scanning probe microscope, which is basically based on the interaction of a probe with the sample surface. Microscopes named as scanning tunneling microscope and atomic force microscope, which are popular example of scanning probe microscope. So optical microscopes are based on seeing an object, and electron microscope is based on developing the image of a specimen, and scanning probe microscope is based on sensing the surface. So the scanning tunneling microscope is based on a quantum mechanical phenomena of tunneling of electron from a tip which is named as cantilever, and it is the tip size of few atoms, and electrons are passing from the tip to the probe surface following tunneling phenomena. So the tip is not in contact with the surface and the study, so the electrons can flow from the tip to the surface and the study only through the tunneling possibility. So the variation in the tunneling current gives us the understanding of surface structures which are down there. So the tip is placed point to point on the surface, and the variation in the tunneling current is being recorded. Well, this microscope has its limitations because if there are some impurity atoms, so they would be seen as an extra structure because of difference in the conduction properties. At the same time, the surface should be conducting. For that matter, again, we have certain limitation on the conduction on the surfaces which can be probed, and we require specific cantilever for specific type of materials as well. Keeping these limitations in mind, the inventors developed a new microscope, which is atomic force microscope, and it is based on optical phenomena, optical reflection of incident light, and upper surface of the cantilever is a mirror which reflects the light towards the detector, and any variation in the angle of reflection, which may be due to which is due to the change in the angle of reflection because of change in the position of the cantilever, would be seen through the detector. And this change in the reflection angle will be providing the information about the surface under study. Due to the optical wavelength regime, we have a limitation of magnification, and at the same time, the tip can damage the surface as well. So, but still, it was a good, remarkable achievement that it is possible to scan surfaces using quantum mechanical phenomena of tunneling, and also using the reflection of light from mirror, which is connected to the cantilever. So, the inventors got Nobel Prize in 1986. Keeping these limitations in mind, we are working on developing another kind of microscope which is based on atoms. So instead of optical fields, we use matter waves, and the matter waves are reflected from an optical surface which is connected to the cantilever, which is being used as a probe on the surface under study. So the atoms which are cold enough, they move coherently under gravity. They move towards the optical surface, which is providing a force on the incoming atoms, and they reflect back. With the incoming atoms interfere and develop the collapse and revival phenomenon. So this is a simple schematic diagram of the suggested microscope which we can develop using cold atoms. So the principle on which the recurrence tracking microscope works is quantum recurrence phenomena. The change in the time of recurrence because of the change in the position of the mirror in the vertical direction gives us the understanding of nanostructures, the size and the spacing of the nanostructures on the surface. So this makes the microscope work. Just showing a few numerical equations, we can write the dynamics of atoms on the electromagnetic field in terms of the kinetic energy and potential energy. So the kinetic energy is simply p square by 2m, and the potential energy which is coming because of two fields, one the gravitational field and the other is the optical field, can be seen as the first term due to the gravitational field and then the optical field. The optical field is having a spatial variation, so as the gravitational potential as well. But the important thing is that this optical potential is now becoming the reason of the reflection, because if we look, we find out that the force which is coming because of the optical field is having an interesting description, which is h bar omega square by delta and u delta and u. Now this delta u is the gradient of the spatial distribution of the field, electromagnetic field, and this delta is the detuning between the field frequency and the transition frequency. Now this delta can be made positive or negative by controlling the detuning required. Now a positive sign of delta would be making the force as repulsive, and the negative sign of the tuning will make it attractive for the atoms. And in our case, the electromagnetic field is having an exponentially decaying profile in the upper direction. And if we take delta to be positive, so our force would be a repulsive force for the incoming atoms. So with this repulsive force, which is coming because of this exponentially decaying evanescent wave field, we find the potential seen by the atom as exponentially decaying because of the optical field, and a linear potential because of the gravitational. Now the cold atoms which are at a certain height in the gravitational field will move in this confined potential and perform the interference phenomenon. Situation can also be built by using magnetic mirrors. So this is also a possibility to replace the optical field by magnetic field and let the atoms bounce back from the magnetic mirror. The suggested microscope works in static and the dynamic mode. I'll present static mode and I will leave dynamic mode for question if there is any. So in static mode, what we see that the surface with the nanostructure is static. So we don't move the surface. So how it is being performed, that as I was saying earlier, that the cold atoms move under gravity towards the optical surface, which is made by the total internal reflection. The atoms observe an exponentially increasing force reflect the incoming atoms. Now these reflected atoms interfere with the incoming atoms and perform collapse and revival phenomena. So what we see that first they have gradually increasing destructive interference, which leads to a collapse of their wave function. So what is simply meant that the distribution would be, once we say that it is completely collapsed, so the distribution of the atoms would be uniformly seen between the upper point and the optical surface. So, and then there is a competition between the destructive and constructive interference. And when the constructive interference is exceeding the destructive interference, we see the cold atoms start rebuilding at the initial phase. And at one time, they are completely appearing the same as they were at time t equals 0 when we started the experiment. And that is named as the revival phenomenon or reconstruction of the initial wave packet. Evolution can also be seen in this view graph because we can see just one and second bounce of the cold atoms from the reflecting surface, that's the optical surface in our case. And we see that the incoming atoms, once they reach the optical surface, they bounce back and interfere with the incoming atom. And we see after the interference, the destructive interference is gradually reducing the possibility of getting the initial distribution at the starting point. So, and once the atoms are again traveling back to the mirror, again we see the interference and the distribution is again smeared up. So it is gradually coming to a complete collapse. So complete collapse would be meaning that we don't have any particular maximas in the probability distribution. So it is seen with many small peaks throughout from 0 to the z0 point, which is the initial starting point. If we want to develop small mathematical description for the problem, so we can write our initial wave packet in the form of a superposition of wave functions. So this is a very simple mathematical relation, and we can calculate the evolution of the atoms over this optical surface by developing a unitary operator. So it's a time evolution operator which takes the initial wave function to any later wave function to any later time t, and we write psi z of t. So if we develop the corresponding equations, it's simple. Our u operator is in this form, and H is already shown previously in the form of kinetic energy, potential energy, and the optical potential, which is composed of optical potential and the gravitational potential. And now this is the expression of the wave function as a function of time t. And if we write the autocorrelation function, so that comes out to be quite a simple expression because it is only a function of time. So the first terms are going to talk about the weighting factor or probabilities of finding the wave packet or atomic wave packet in the nth state, and then we have ENT divided by h bar in the exponent, which is basically corresponding to the frequency. So here we have a simple description of autocorrelation function which provides us the evolution in time. So if we want to understand this expression, we may write in the real and imaginary part, open the exponential function, and let's talk only the real part. So the real part would be the cosine of omega nt minus real part would be cosine of omega nt multiplied by cm mod square, summed up over all n values. If we pick up just one n equal to 1, we find out that this is a cosine wave which is moving with a certain frequency as a function of time. If we pick up next term and add that up with the first term, so we find that as a function of time there is some interference phenomena because of these two terms which are moving with their own frequencies. If we sum all these terms together, we find a very impressive interference of waves, and what we observe that at various different times, so horizontal axis is that of time, there is some reappearance of the peak structure, and at some particular time there is a very pronounced peak which is higher than any previous value. So this higher peak is considered or can be named as the time of revival, and at this particular time our initial wave packet is seen at the initial point from which it was launched, was propagated with almost the same initial distribution in which it was. So this time is named as the time of revival, and this is the subject of our interest. If we calculate this, it comes out to be function of initial height. So if the initial height is large, so the time at which the revival takes place would be large, and if it changes, so the time would change. So the time of reconstruction would change. The two different initial heights of the cold atoms above the mirror that may happen because of movement of the mirror in the upward direction, we find out that the time of reconstruction is changing, and that becomes a key thing in the development of this recurrence tracking microscope, because as the cantilever is connected with the optical reflecting surface, so the movement of the mirror due to the cantilever going up and down on the surface and the steady due to the nanostructures would be seen as changing initial height of the atomic mirror above the initial height of the atoms above the optical surface, and that change would be seen in the appearance of the quantum revival phenomena. So this would be the change can be measured by changing time of revival, and this will be providing us a value of the modified z value, and that will be providing an information of the structures down there. So just conclude my talk up here, and I wait for any question if there are. Thank you.